Okay, so now we're going to take a look at vectors in 2 dimensions. Everything we've done before now would be that we've isolated it pretty much to just one dimension, primarily on the x-axis or the horizontal axis. Now we're going to look at the horizontal and the vertical axis and see how it plays out when we have to deal with vectors on both of those axes. So we're going to look at the properties, the components, and then we're going to come back to our friends displacement, velocity, and acceleration, but now in 2 dimensions, and learn how we combine them together to come up with something called the resultant. We're going to look at motion in 2 dimensions and then relative velocity. So we need some definitions here. First off, let's look at the term scalar. Scalar is a quantity that can be completely specified by its magnitude with appropriate units. Okay, so you see from this direction, a scalar has magnitude only, but no direction. Okay, so at like 66 miles per hour. 66 miles per hour tells us nothing other than how fast a car was going. Was it going north, east, west, south? What direction was it going? So we're going to differentiate now between scalars and vectors. Scalars can be manipulated using ordinary arithmetic. For example, liters is a scalar. 2 liters plus 3 liters is 5 liters. There's nothing more than magnitude represented here. The vector, on the other hand, is a physical quantity that requires the specification of both magnitude and direction. So we're going to start looking at, these angles that are going to be made. How do we determine which way it's going and with what velocity or acceleration? Force and velocity are examples of a vector. So the magnitude and direction are needed to understand the force or velocity. Looking at equality of vectors, 2 vectors, A and B, so we've got the red one and the blue one, are defined as equal if they have the same magnitude and the same direction. This property allows us to translate a vector parallel to itself in a diagram without affecting the vector. And this will become important because if we move components up or down, left or right, and we don't change anything about the angle and the magnitude, then we've been able to translate the vector parallel to itself anywhere on the axis. And we'll primarily start off with the Cartesian or the rectangular coordinate system and then move to the polar coordinate system. So if we want to add vectors together, we can bring the components into a diagram. When 2 or more vectors are added together, they must have the same units. So the resultant, or the combination of these vectors, we call R, the resultant, is given by the vector sum of A plus B. So we've got a vector along the horizontal axis, we've got a vector along the vertical axis that has an X and a Y component. We're going to learn more about that. When a vector B is added to a vector A, the vector sum R, which is primarily this long one here, since this isn't a right triangle, that's not the hypotenuse, but if it were a right triangle, that long one would be the hypotenuse. The vector that runs from the tail of A, okay, there's the tail of A, to the tip of B, which is over here, is the resultant. Okay, here the resultant runs from the tail of B to the tip of A. So these constructs then prove that A plus B equals B plus A. Because if you look at B here and B here, it's parallel. If I look at A here and A here, it's parallel. So this resultant remains the same between the two. This is known as the triangle rule of addition. The other rule that we look at is something called the parallelogram rule of addition. Okay, you'll notice what we did here is we took our original problem, A and B, and we took the B vector and moved it parallel to itself and with the tail along the A vector. So in this construction, the tails of vectors A and B are joined together, and the resultant vector R is the diagonal of the parallelogram formed between A and B and its sides. So this is the kind of thing, once you get to your lab and you do the vector lab, this is what you're going to be looking at, because you're going to have strings that you're going to be putting weights on and building these vectors on a force table. We can do the same thing with multiple vectors here. We're going to add vectors using a geometric construction summing of 4 vectors. So we have vector A, we still have vector B, though it's a little shorter, C and D, and then we have a resultant. So what this is telling us is if we were traveling along a path let's say due east, vector A would be from 0 to some point. And then we changed directions with vector B and we went northeast, our northeast path would be B. Then we changed directions again and went northwest, that would be C. And then if we changed directions one more time and went northwest again, but at a different angle, when we summed A, B, and C together using its vector components, we would get this resultant A plus B plus C plus D. So a geometric construction for summing the 4 vectors becomes the component addition of each of these vectors. A can be broken down into its 2 components, sine and cosine. B will broken down to its components, sine and cosine. C, sine and cosine. D, sine and cosine. And when we add all the sine components together and add all the cosine and sine components together individually, then we would get this summation or resultant. So the geometric construction for summing 4 vectors then forms the resultant vector R, and this vector then completes the polygon. Notice here now we've got 2 vectors, same length, same magnitude. One is negative, one is positive. The negative of a vector is defined as the vector that when added to A gives a 0 sum. So if we went all this distance on A and then went all the way back this distance on negative A, of course you can see that we have A plus negative A equal to 0. Okay? They have the same magnitude but in opposite directions. Okay, so one negates the other. We would say that we have a net displacement then of 0. Looking at subtraction of vectors, vector subtraction then makes use of the definition of that negative vector. We define the operation A minus B as vector minus B added to vector A. Okay, so A minus B equals A plus A minus B. So again, you can see here we have vector A, we would have vector B up here, the dashed line, or we would have the negative B, the solid line, and then the A minus B over here would end up being the summation of those 2, or the subtraction, the difference between them. Vector minus B has the same magnitude as vector B, but points in the opposite direction. If we look at multiplication and division of vectors times a scalar, so we're taking a vector and we're multiplying it by a scalar amount. The multiplication or division of a vector by a scalar amount now gives us a vector, because we've taken the product or the quotient and affected the original vector. For example, if a vector A is multiplied by a scalar number 3, the result would be written as 3A, or 3 times A. There's a times sign understood. And it's a vector with a magnitude 3 times that of the original vector A, pointing in the same direction. So this one would be A, this would be 2 times A, and this would be 3 times A. So the multiplication or division of a vector then is a scalar times or divided by that scalar. So let's take a look at an example. We've got a trip here, a car trip. A car travels 20 kilometers due north and then 35 kilometers in the direction 60 degrees west of north. Find the magnitude and the direction of the car's resultant displacement. So if we draw this out as a graph, and you can do this in Excel and have some fun with it. because we can define all these vectors in Excel, and you're going to do that if you're in my lab class. Okay, so we have vector A. You can see here that it moves in the y direction 20 kilometers. Okay, so it's straight north. And then B, we moved 60 degrees off of the y-axis in a direction that accounts for 35 kilometers. Okay, so you can see here we have a resultant. This is your net displacement, or your real distance traveled, A and B. So the problem can be solved geometrically using graph paper and a protractor. The resultant displacement becomes R over here. So you can see it's going to be in the negative direction on the X or horizontal axis. The resultant displacement is the sum of the two individual displacements A and B. The length R, then drawn to the same scale as A and B, and you have to be careful to make sure you set up your scale properly, indicates that the displacement of the car is actually 48.2 kilometers. The measurement of the angle beta shows the displacement is approximately 38.9 degrees west of north. So we've got two vectors here that we've added together vectorially and is shown in the resultant R. Okay, so when we come back, we're going to take a look at how we can decompose our vectors into something called components.